Hereditary stomatocytosis is a severe blood disorder where a patient's red blood cells mutate into warped cup-shaped structures. To treat the resulting anemia, doctors often rely on a standard high-stakes procedure. They surgically remove the patient's spleen. But the surgery produces entirely contradictory results. For a large portion of patients, removing the spleen acts as a near-perfect cure. Their red blood cell count recovers, and they go on to live healthy lives. Yet for others with the exact same condition, the exact same surgery triggers sudden, massive blood clots that can easily become fatal. Look at this comparison. Cells from cured patients sit beside cells from patients who developed fatal clots. To the human eye, they share an identical structure. One is slightly more cup-shaped, the other resembles a coffee bean, but both look like the exact same disease. Because doctors cannot predict how a patient will react based on the shape of their cells alone, recommending a splenectomy has remained a blind gamble. To figure out why the surgery kills certain patients, we have to stop looking at static images of cell shapes and start mapping the physical forces acting on them in motion. Researchers use a digital physics tool called dissipative particle dynamics. Instead of a flat picture, this creates a three-dimensional molecular-level simulation of the blood cell, allowing us to measure its exact mechanical flexibility under the pressure of flowing fluid. Subjecting the cells to these fluid dynamics reveals that they belong to two completely separate mechanical classes. The first type is physically swollen and overhydrated. The second type is severely dehydrated, making its outer membrane incredibly stiff and rigid. Outward appearance is a biological decoy. The structural flexibility of the cell is the true variable dictating whether a patient will survive surgery. To understand why flexibility matters, we have to look at how blood physically navigates the spleen. It operates as a relentless mechanical filter, forcing every single red blood cell through narrow interendothelial slits that are only 1 to 2 micrometers wide. In this simulation snapshot, we can clearly see the overhydrated, swollen cells, colored in blue, failing to squeeze through the tight gaps. They violently jam the parallel slits, creating a massive upstream traffic jam that destroys the cells and leaves the patient dangerously anemic. When surgeons remove the spleen in these overhydrated patients, they are simply removing the bottleneck. The cells flow freely through the body, and the anemia is cured. The rigid, dehydrated cells behave entirely differently. Their specific coffee bean geometry actually allows them to slip through the spleen's narrow slits without jamming the filter. This bar chart measures the exact transit time of that crossing. The rigid cells clear the slit, but they take nearly 3 times longer to do so than a healthy cell. That slow transit time leaves the cells exposed inside the spleen for so long that the organ's resident macrophages recognize them as defective and quietly consume them. For patients carrying dehydrated cells, the spleen isn't causing a dangerous bottleneck. It is a vital, functioning holding pen, deliberately trapping and destroying stiff cells before they can cause damage elsewhere. So, what happens to the rest of the bloodstream when a surgeon removes the spleen of a dehydrated patient, suddenly unleashing thousands of rigid cells into the body? Healthy red blood cells use a mechanic called tank treading. Under the shear stress of moving fluid, the cell membrane physically rotates around the fluid inside it, like a treadmill. This allows densely packed cells to slide past each other. But dehydrated cells have stiff membranes and cannot tank tread. Instead, they tumble awkwardly, physically locking together and colliding with healthy cells in the bloodstream. Looking at this graph, the result is clear. At low flow rates, these tumbling cells spike blood viscosity by 30%. As the 3D inset shows, this creates dense, congested clusters, driving massive blood clots in the veins following surgery. The surgery kills these specific patients because removing the spleen destroys the exact filtration system required to keep their blood thin enough to survive. To prevent these fatalities, clinical doctors need a reliable way to measure the exact physical flexibility of a patient's cells before approving a splenectomy. Biophysicists have designed a microfluidic pathway called the FOR chip to do exactly that. The chip forces cells to flow down a narrow, fluid channel blocked by a single semicircular obstacle. Soft, flexible cells smoothly bend around the obstacle, allowing the fluid forces to push them directly back into the safe center lane of the channel. Look at this trajectory graph. Stiff cells lack elasticity to wrap around the pillar, ricocheting outward from the center lane. These plotted offsets give a strict mathematical signature. Without using chemical dyes, doctors can read the exact displacement distance to instantly identify dangerous rigidity. By pushing a single drop of blood through this microscopic chip, a doctor can instantly determine if a patient has the rigid cell type, stopping a high-risk surgery before it ever begins. By looking past the nominal morphology and measuring the internal bending rigidity of these cells, we can update the clinical approach to stomatocytosis. It moves from a surgical guessing game into a triage system grounded in fluid mechanics. If you found this dive into biophysics fascinating, leave a like, subscribe to the channel, and let us know in the comments what medical mysteries we should cover next. Today's video was brought to you by Synestex Systems LLC, founded by Shane Persinger. Understanding the mechanical forces within the human body allows us to resolve the microscopic failures that standard medicine misses. Thanks for watching.